Hello, welcome to another module in this massive open online course on estimation for wireless communications. So, we are looking at equalization, and we said equalization is necessary for a wireless communication system or a wireless communication channel in which there is inter-symbol interference, right. So, just to refresh your memory, we looked at a system model in which the received symbol is yk equals h0 times xk plus h1 times xk minus 1 plus, well, Vk, where Vk is the noise. We said this is the received symbol at time k, this is the received symbol at time k, this is the transmitted symbol xk at time k, transmitted symbol at time k, and xk minus 1 is the previous symbol transmitted at k minus 1, previous symbol. Previous symbol transmitted at time instant k minus 1. Therefore, yk depends not only on xk, but there is also, it depends also on xk minus 1. There is interference in the detection of xk from xk minus 1. That is xk minus 1, which is the previous symbol, is interfering with xk, which is the current symbol. This is known as inter-symbol interference, correct. So, this phenomenon is basically termed as ISI or inter-symbol interference. Inter-symbol interference, and also here we said we are considering a two tap channel. This H0, H1 are the taps of the channel. So, H0, H1, basically we have said this is an L equal to 2 tap, 2 tap channel, that is H0, H1 are known as the taps of the wireless channel, and we have 2 taps, that is H0 and H1. So, the number of taps is L, which is equal to 2. For a general L, we have H0, H1 up to HL minus 1, that is L tap, that is the L tap wireless channel, for which the taps are denoted by the coefficients H0, H1 up to HL minus 1. And we said we want to remove this inter-symbol interference. This inter-symbol interference degrades the performance of communication. Therefore, we want to remove inter-symbol interference at the receiver. This is termed as equalization. So, we said we would like to ISI this inter-symbol interference degrades or results in loss of performance, degrades the performance ISI removal, that is removal of ISI or inter-symbol interference, and this is actually what is termed as your equalization. Remove of ISI, the inter-symbol interference, is termed as equalization, or more, it is also known as channel equalization. Formally, it is known as channel equalization, also simply termed as equalization, alright. That is basically removal of the inter-symbol interference, right. And we said for removal of the inter-symbol interference, we are going to use 3 received symbols, that is we are going to build, that is we are going to employ a 3 tap equalizer. So, an equalizer is employed for equalization, okay. So, equalizer So, equalizer is basically the filter that is employed for equalization. We said we are going to employ received symbols yk plus 2, yk plus 1 and yk for equalization, that is we are building a 3 tap, that is R equals 3 tap equalizer. Yeah. So, we said we are going to use 3 symbols, that is yk plus 2, yk plus 1 and yk, that is the number of symbols that is used for the purpose of equalization is R equals 3. Therefore, this is also known as a 3 tap equalizer. Alright. So, now let us write the equations for these received symbols yk, yk plus 1, yk plus 2, and that also is something we had written last time. So, yk equals h0 xk plus h1 xk minus 1 plus vk, yk plus 1 equals h0 xk plus 1 plus h1 xk plus vk plus 1 and yk plus 2 is h0 xk plus 2 plus h1 xk plus 1 plus vk plus 2. Yeah. So, basically now we have written the equations for yk, yk plus 1 and yk plus 2. So, we have written the equations for these 3 symbols. Now, look at that, yk depends on xk and xk minus 1. So, yk plus 1 will depend basically on xk plus 1 and there will be interference from xk, which is the previous symbol, to xk plus 1. Similarly, yk plus 2 will depend on the transmitted symbol xk plus 2 and there will be interference from the previous symbol, that is xk plus 1 and so on. So, therefore, this is the model that we are employing, that is the intersymbol interference model. Now, we are going to write these yk plus 2, yk plus 1, yk as a vector. So, I am going to write these as a vector. So, once I stack these as a vector, I have yk plus 1, yk plus 2, yk, which is equal to, now you can see this can be written as the matrix h0 h1 0 0 0 h0 h1 0 0 0 h0 h1, this is the matrix H times the vector xk plus 2, xk plus 1, xk, xk minus 1, yeah, plus the vector plus the noise vector, which is vk plus 2, vk plus 1 and vk. And now, we call this as the vector y bar of k, which has yk plus 1, yk plus 2, yk. This we call the matrix H. So, y bar of k, this is your r cross 1 vector, that is in this case r equals 3. So, this is 3 cross 1. H is basically r cross r plus L minus 1, r equals 3. So, this is 3 cross 3 plus L equals 2, 2 minus 1, which is equal to 3 cross 4 matrix. This is x bar k, which is basically r plus L minus 1 cross 1. So, this is r plus L minus 1 cross 1, which is equal to 4 cross 1, and this is your vector v bar of k, which is r cross 1, that is basically a 3 cross 1 vector. So, I have the system model. Now, I have converted this into the vector form, in which I have the system model y bar k equals the matrix H times x bar k plus v bar k. Okay. So, let me write that. I have y bar k equals H times x bar k plus v bar k. This is the, what is this? This is the vector model for the ISI channel, that is communication channel with, for ISI channel, or ISI means basically inter-symbol interference, that is a communication channel with inter-symbol interference. This is the vector model for the communication channel with inter-symbol interference. Now, we are going to have to design the equalizer. Remember, we are designing a 3 tap equalizer, that is r equal to 3. So, let the taps of the equalizer be denoted by C0, C1, C2. So, let the taps of the equalizer be C0, C1, C2. This can be denoted by the vector C bar equals C0, C1, C2. So, this is also your equalizer vector. You can think of this as the equalizer vector. What is the equalizer vector? That is an r dimensional vector which has the taps of the equalizer, that is C0, C1 up to Cr. Since we are considering r equal to 3 tap equalizer, we have C0, C1 up to C2. These are the 3 taps. Okay. Now, as we said last time, what does the equalizer do? Essentially, it takes a weighted linear combination of the output symbols yk plus 1, yk plus 2. Alright, and basically with that weighted linear combination, we would like to eliminate the inter-symbol interference on xk. And how do we do that? So, we take a weighted linear combination of yk plus 2, yk plus 1 and yk, and this we do as basically the weighted linear combination is, this is given as C0 times yk plus 1 plus C1 times yk plus 2 plus C0 times yk plus 2, C1 times yk plus 1, C2 times yk. So, this is the weighted linear combination that we are performing to remove the inter-symbol interference on xk. Okay. So, we are performing this linear combination, let us put it that way. To remove the interference, we are performing this weighted linear combination to remove the interference for xk, and therefore, now I can write this as, look at this, I can write this linear combination as the row vector C0, C1, C2 times the column vector yk plus 2 yk plus 1 times yk, that is the row vector C0, C1, C2 times the column vector yk plus 2 yk plus 1 yk. And now look at this row vector is nothing but C bar transpose, that is transpose of the equalizer vector times y bar of k. So, this is basically C bar transpose y bar k. So, basically this is C bar transpose y bar k, this is the equalizer operation, this is the equalizer So, the operation of the equalizer, basically what does it equalizer doing? It is performing a weighted linear combination of the symbols yk plus 2, yk plus 1, yk, alright, and that is C0 times yk plus 2 plus C1 times yk plus 1 plus C2 times yk, which can be expressed as the equalizer vector C bar transpose, that is the row vector C0, C1, C2 times the column vector y bar k, which is yk plus 2, yk plus 1, yk. Now, if I substitute the expression for y bar k from above, look at this, I have already derived the expression for y bar of k equals h x bar k plus v bar of k. So, now substituting y bar of k equals h x bar k plus v bar k, I have C bar transpose y bar of k equals C bar transpose h x bar of k plus v bar of k. Now, removing the brackets, I have C bar transpose h x bar of k plus C bar transpose v bar of k. Now, let us look at this quantity C bar transpose h x bar of k, which is basically equal to some row vector times x bar of k, which is x of k plus 2, x of k plus 1, x of k, x of k minus 1. This is basically your x bar of k. So, I can write C bar transpose h x bar of k as some row vector times the column vector x bar k. Now, the question is, what should this row vector be? What should this row vector C bar transpose h be? So, if I look at this row vector, what should this, and I ask the question, what should this row vector be? Ideally, this row vector should be 0, 0, 1, 0, so that when I multiply this row vector by x bar of k, I get 0 times x k plus 2 plus 0 times x k plus 1 plus 1 times x k plus 0 times x k minus 1, which is x of k. So, we actually desire, let me write this clearly, we desire or we would like or we and this is an important note. So, it is important to understand this point. See, we have C bar transpose h times x bar k. Now, how should we design the equalizer C bar? Ideally, we would like C bar transpose h to be the row vector 0, 0, 1, 0, so that when it is multiplied by x bar of k, the interference from xk plus 2, xk plus 1 and xk minus 1 is removed, and what we are left with is xk. So, ideally we desire C bar transpose H equals 0 0 1 0. Now, we might not get that exactly, that is C bar transpose H might not exactly be 0 0 1 0, but if not exactly, then we would like to at least approximately as closely as possible. That is the idea. So, C bar transpose H, if possible, should exactly be 0 0 1 0, if not possible exactly, then at least to the best possible approximation it should be close to the vector 0 0 1 0, and that is the point between equalizer, that is we want C bar transpose H equals this thing or as best approximation that is C bar transpose H should approximate 0 0 1 0 as best as possible. Therefore, what we desire is 0 0 1 0 should be approximately equal to C bar transpose H. Now, taking the transpose on both sides, that is taking transpose on both sides, we have 0 0 1 0 transpose equal to C bar transpose H transpose, or basically approximately should be approximately equal to this quantity. Now, therefore, if you take the transpose, of course, the row vector will become the column vector. Therefore, I can have 0 0 1 0 should be equal to, well, or should be approximately equal to C transpose H transpose times C bar. Yeah. So, what we should have is this column vector 0 0 1 0 should be very close to H transpose times C bar. H transpose times C bar should be as close as possible to 0 0 1 0, and naturally we have already seen a framework to do this, that is to minimize the squared error. That is, when we want the approximation to be very good, what we would like to do is to basically decrease the error as much as possible, which means basically we have to consider that vector C bar which gives the least norm of the error, and that leads us to the least square solution. So, what we would like to do in fact is basically we would like to, if I denote this vector by 1 bar of 2, or if would like to denote this vector appropriately by, let us say, this notation 1 bar of 2, basically what this is, look at this, this is has a 1 in the second position. If we call this as the 0th position, this as the first position, this as the second position, and this as the third position, this has a 1 in the second position and zeros elsewhere. So, this is then denoting with the vector 1 bar 2. So, 1 bar 2 must be approximately equal to H transpose C bar, which means minimize, which means I have to minimize the error one bar 2 minus H transpose C bar. Of course, 1 bar 2 is a vector, H transpose C bar is a vector. So, when I say minimize the error, since this is a vector, I have to look at minimizing the norm of the error, or norm of the error, or the squared norm of the error. If I minimize the squared norm of the error, it is the same thing as minimizing the norm of the error. So, basically that now gives rise to the least squares cost function, and that is it. So, equalizer C bar, so best equalizer C bar which is best equalizer C bar is best equalizer C bar, what does it do? It minimizes, that is it is the minimum of 1 bar 2 minus H transpose C bar whole square. That is, the best equalizer C bar is such that H transpose C is as close to this vector 0 0 1 0 as possible. So, we are basically considering that C bar which has the least error, so that is which minimize the error 1 bar 2 minus H transpose C bar, that is basically the least square solution. And now you can see this is indeed the least square solution, because look at this H, size of H is 3 cross 4 implies H transpose is 4 cross 3 matrix, implies H transpose has more rows than columns. H transpose, the matrix H transpose has more rows than columns, therefore H transpose is a tall matrix, and this is exactly the kind of problem for which we have the least square solution, right. So, we have, remember previously we had y equals x times H bar, in which the pilot matrix H had more rows than columns, that is more observations than the antennas, and here we have something similar except in a slightly different context, that is in the context of equalization. For instance, if I have to draw a parallel, not an exact parallel, but just simply in the perspective from the point of view of least squares, I had y minus x H bar norm square, and the solution was basically your H hat equals x transpose x inverse x transpose y bar, that is the least square solution. Now, all I am doing is replacing my y bar by 1 bar 2, x is equal to, so my y bar, so in this example for equalization y bar is basically your vector 1 bar 2, your vector x is nothing but the matrix H transpose, and I am trying to estimate C bar which plays the role of H bar here. So, my my equalizer C bar is basically H transpose times H transpose inverse times H transpose 1 bar 2, that is the least square solution, and that C bar is equal to H transpose, C bar is equal to H transpose inverse H times 1 bar of 2. This is the solution of the equalizer. Now, you can see this is the solution of the, this is basically your equalizer, that is C equalizer C bar. This is basically the equalizer C bar, which is H transpose inverse H transpose H times the vector 1 bar 2. This is basically the equalizer, and we have already defined the matrix H earlier, right, and 1 bar 2 is also the vector that we have defined before. But anyway, just to again confirm that, just to again remind you, 1 bar 2 is the vector 0 0 1 0, and if you remember, H is this matrix which is formed from the channel coefficients H0, H1 0 0, 0 H0 H1 0 0 0, and this, and substituting we get the equalizer which is C bar. And once you have the equalizer, the resultant equalized symbol x hat of k, remember x hat of k, that is equalized symbol x hat of k equals C bar transpose y bar of k, which is basically now you can see that is equal to C0 times yk plus 2 plus C1 times yk plus 1 plus C2 times yk. This is the equalizer. So, this is the this is how you equalize, that is you design C0, the taps C0, C1, C2 as H transpose inverse times H into this vector 1 bar of 2. Now, once you get the tap C0, C1, C2, you use them as weights to linearly combine yk plus 2, yk plus 1, yk as C0 times yk plus 2 plus C1 times yk plus 1 plus C2 times yk to get an estimate of the symbol x hat of k, and basically that explains equalizer. So, what we have done is, interestingly, basically we have looked at this model for intersymbol interference of a simple L equal to 2 tap wireless channel. Right, we have modeled it, we have extracted the vector model for this intersymbol interference channel, and then we have motivated this equalizer design to remove intersymbol interference at the receiver, and we have also demonstrated that this equalizer design can be demonstrated, can be reduced to a least squares problem, that is basically where we have demonstrated that this is the best equalizer C bar minimizes the error 1 bar 2 minus H transpose C bar, that is minimizes the squared norm of this error, and this equalizer C bar is found as the least squares solution. And of course, now we have considered a simple channel with L equal to 2 taps. Naturally, you can extend it to a more general channel with L taps, and of course, a more general equalizer with R taps. Here we have considered R equal to 3, but of course, you can again extend it using this. Based on this example, you can in a straightforward way extend it to a scenario with any arbitrary number of taps R. Alright. So, this basically comprehensively explains equalizer design. This is also known as the design of a zero forcing equalizer. That is probably worth mentioning. This explains the design of a zero forcing equalizer, and we will look at an example in the next lecture to understand this better. Thank you.